afternoon. It's afternoon here in Brussels. I don't know what your time zone is, but here it's an afternoon, a little bit rainy in Brussels. So I will go out on the bike later when it's dry. This is another video. I have a few on my channel. Every time I make a video, I think it's sort of my last one, but then there's something that I think like, oh, well, you know, I should do something about that. This video in particular actually was triggered by some questions I got on a previous video and previous papers also from two people. I will not name them, but they made me realize, like, you know, I will address myself a video, put some things on slides and try to explain why I actually do not agree with the way they are proceeding on their search, I would say, for you know, models. One is actually an older man who's very intrigued. He sent me a book. He quotes me a lot as a source of inspiration for his book. At the same time, he is obviously trying to reduce and simplify further by looking like beyond charges and fields, because basically everything I do is like we have charges and fields. In low energy physics, high energy physics is a bit complicated because there you have you know, this strange thing of electron positron, you know, charged pairs that annihilate each other or get created out of fields. It's a very mysterious thing, but that's probably the only mystery left, I think, in quantum mechanics. But so he's pushing, like, you know, we should reduce this further, charges, fields, and then he gets into some kind of quantum theory of the vacuum, where I'm going like, no, that's not me. I'm not space-time is space-time, it's a vacuum. Of course it has like properties, but these are not like material physical properties for me. You know, we have electric permittivity, magnetic permeability, but I'm not ontologizing space-time. I'm not going there. So, and that brought me to another thing. I got a question from someone who says, look, I'm trying to make sort of you know, I'm bringing a lot of people in touch, and your theory is of course just one of these many theories that look for some kind of unified approach. And so he wants actually to make a wiki like on ether theories, modern ether theories, where I'm also going like, no, that's not me. I don't want to be on your wiki. My theory is not about ether. It is what is written there. I call it the realist interpretation of quantum mechanics. It's grounded in classical physics. For me, basically all of physics is sort of at a dead end, because we do have a very logical explanation for everything, I feel. Antimatter, even dark matter, I will come back to that. You know, how charges and fields work, what light particles are, like neutrinos and photons. The electron-proton structure, we have models for that, particle models that explain their radius and their size and their magnetic moment and even the anomaly in their magnetic moment, all these kind of things. So so I don't want to go where these people are going, and I want to make it clear in this video what I think about, yeah, reality. You know, what is relative? Absolute is our relative things we measure, like mass and energy. Are these real? Of course they are real. But I want to sort of make clear I would say the philosophical foundations of what I'm doing, and surely, as said, what I'm not doing. While making the slides, I realize actually I'm very much more mainstream than I thought I was. So that's good news. I quote Boltzmann there again. So I do believe what I'm talking about is not to self-aggrandize myself or you know, get an audience, or I'm an amateur physicist. My background is in economics, econometrics. I did not finish a PhD, but I have a Doctor of Science, Doctorandus title in that. because you do get to you do learn a lot about modeling, which helped me greatly. Systems of equations, equilibrium and disequilibrium situations. And I did philosophy. I have a bachelor's in philosophy as well, which also helped me greatly, I think, to make sense of a lot of theories. Okay, so let me start by showing this. Actually, I think for all amateur physicists out there, it is very important that you don't go off theorizing, based on some intuition, based on a bit of reading, but not a lot. I think you really need to go all the way, and especially sort of every time, and that has happened a lot in the last 20 years, I would say, when something major happens, like this discovery of the Higgs boson. Look at what they found. Look at what you see in these experiments. I'm the first one to say that the particle zoo, all these unstable resonances, I would say, or unstable particles that are very short-lived, especially the Higgs boson. It's massive, and its lifetime is so short it can barely travel a few millimeters. So there's a lot of theorizing around that, and then I always go back, like, show me the pictures. So the evidence we have, and that's where I go and try to ground my theory, is what we see is particles, stable particles with enormously high energies. So in this case, there were two protons that were accelerated at a velocity of almost the speed of light. It's impossible to accelerate them at the speed of light because they have a mass. Then the energy you would need for that would be infinite. But yeah, when you give them an energy, kinetic energy, 7 to 8 tera electron volts, that's huge, huh? That's enormous, especially because the proton is so small. So loading kinetic energy on a proton to give it that velocity, that energy is huge. But what you see is sort of, there's a big collision, and in the end, what happens? We get various pathways of disintegration, and then these unstable things, they recombine in something that is stable again. Which in this case, like muons are actually not stable, but then these disintegrate further. But that's the tracks we have. We have gamma rays emerging from these detectors. We have muons emerging from these detectors, and then they go then they get captured, or else they continue a while and break down again in more stable constituents. So that's what we see, and that's where I immediately want to say, like, I'm not a believer in quark-gluon theory or virtual particles and a lot of stuff. I made that very clear in my previous video. But I do believe these experiments are real, and so when you want to come up with something else, then you had better phrase it in terms of gamma rays, photons. What are they? What's their signature, so to say? What's their structure? How do you think of them? And how do they shake hands with other things, or how do they disintegrate exactly into something else? I have another slide here where I always say that too. Go to the particle data group website where we're actually you see these experiments as well, and we know that this image is a bit in trouble now because there's absolutely no idea of 10 years ago people discovered there's dark matter out there, and dark matter, you cannot sort of explain it by anything that's on the screen here except where is it? Axions would be some kind of new mysterious particle, or maybe there's another type of Higgs boson or whatever. I think there's a very easy explanation for dark matter, a classical one, which I will explain. But I do urge people to look, what are they measuring here? And I'll immediately give the example of, photons. Look at it. These experiments are interesting. How low can their energy be? What is sort of the smallest energy value for these things? So you look at these experiments, and then you get a better feel for what is being measured. And I think when you build a theory, you really have to have a bit of a you have to study these things, and you have to see what is actually being measured there, and how do we then try to explain it I'll show the other one. This is an interesting one on the PDG website, where lately there have been some experiments where people think like, well, the photon, we think it has no charge. It's an uncharged particle. But maybe it has a very, very, very tiny charge. And I think this discussion is related a little bit to, neutrinos. They're also like light-like particles, huh? They travel at the speed of light, but people then discover maybe not quite at the speed of light. Maybe they have some rest mass, unlike a photon. And so where does that come from then? Does it come from some kind of charge? I think it comes from, in the case of neutrinos, it's a different type of oscillation than a photon. And I will talk a little bit about that. But really, and I will say to everyone here, when you write me, I will probably point you to things like this and say, like, have you looked at this? And is this sort of what what can you add? Show me your equation. Show me the experiment that sort of confirms where your new explanation, everything is energy. Yes, everything is energy. Of course, everything is energy, but we have potential, kinetic energy, even potential energy. You need to distinguish between the energy in the field, potentials, and then what kind of notation do you use? Is it pointing vectors, or what do you think in terms of a vector potential, scalar potential? You really need to sort of go down to that level to convince me to seriously look at your theory, and then understand what I'm trying to say also when you think my stuff might or might not be interesting. So this is a general picture I often give to people who come like with papers with a lot of text and a lot of verbosity, I would say. So it's like, give me equations, and these equations need to be phrased in things that are real and that we can measure. Because basically, I'll come back to my definition of reality. Reality is that what we measure. There's no room for uncertainty or what can you measure, what comes out of it, but we're measuring something that happens in a system. And then, of course, because the velocities are so high or whatever, maybe we don't know the initial conditions of that system. And that's probably where uncertainty comes in. If you don't know the initial conditions of the system, then you cannot predict exactly what's going to happen. But the system itself is determined, and what you're left with is a statistical determinism then. But to come back, these are the fundamental categories really. And so we measure things. Everything is motion, I often say. Charge in motion. Traveling fields, there's static fields of course as well, but even those static fields, we will measure those in space, and that's a three-dimensional space also, to be very clear when people want to categorize me. And people also saying like, look at my theory, I've got a space with 11 dimensions and I get everything out of it, and it's sort of and I say like, first, that's not very flat. 11 dimension is a lot. I basically think a few fundamental constants in nature, and then a very limited number of fundamental equations, Maxwell's equations, the Planck-Einstein relation, Einstein's energy mass equivalence relation, that will do, so there's not so many degrees of freedoms or equations to choose from, and there's also not so many constants to choose from, and so the stuff we can do with that is limited, and is you basically arrange it in something like that, where you tell me what is moving, and explain to me that, and of course, in taking account of relativity theory, we measure something in our reference frame, so a number of things when will change when your reference frame changes, and these are the things that change then. Energy, momentum, these are relative concepts, but they're very real, of course. We measure real linear or angular momentum in our frame of reference, and the fact that the measurement comes out a bit differently when we're in different reference frame doesn't mean there's nothing real. So what's real is the idea of a force, and energy is sort of a formless concept. It's force over a distance. That distance can be a linear wavelength or linear length. It can also be something that goes around, spins around. There's energy in all kinds of oscillations, and these oscillations can be, happen in 2 dimensions or 3 dimensions. But that's it. It's in 3D space. You need to show me and tell me what is it that you think is oscillating there, and how exactly so that do you pack then a certain amount of energy in that thing that is oscillating or moving around. So, and that you need to show what is the force that is acting on that thing, and over which distance is it going. That's how you measure energy. Momentum is force times time. Its physical dimension is Newton seconds. So that's a force acting on something during some time. And so energy, momentum, they're on the left and the right hand side of this triangle. The thing that brings all together is this weird concept that is really underexploited and misunderstood, and which I think should be much better explained at the level, secondary school level. Just like complex numbers, complex notation, these are topics that for some strange reason, you do not learn when you're 14 or 15. And action is, for me, it's a very clear concept. It's a force over times the distance times some time, and it's the same dimension as angular momentum, something that goes around and around and around, or any kind of perpetuum mobile, because most models are sort of perpetuum mobile, a system that moves, that has some energy, that packs some energy, but it also packs some action. So these are the fundamental concepts, and I think everything can and must be reduced to these to that, except one thing that is not shown here is a force needs to act on something, and that's then the question, what does it act? Does it act on mass? No, well, yes, of course it does. At the macro scale, gravity acts on a mass and this and that, but at the micro scale, the smallest of small scale, there's really only one force, I think, and that's the electromagnetic force, and it acts on a charge. Then we have fields, of course, but the field is like, that's a force without a charge to act upon. That's a more abstract concept. It's also very real. Charges and fields are very real. But that's sort of where, you make abstraction of your force concepts, and we're talking light particles instead of matter particles, because matter particles are charged particles. Even neutral matter particles like a neutron, we think of them as consisting of some, positive and negative charge. But that's what it is. I want to say one thing here that I have probably in the symbolism, notations, wave function, math, and whatever, I have not emphasized enough. Is sort of the nature of the arrow of time. Let me be very clear. I use it in my notation also, say like you can look at a positron as an electron that moves backwards, both in space and in time. But that's really a metaphor. That's a mathematical thing. Of course, this positron is going to move in the direction that it is moving to, annihilate with another electron, and it is moving forward in time. So time has one direction only, and that's also where I feel I have not stressed that enough. People think like, oh, we have this very special space-time fabric, or whatever you want to call it. Yes, space-time fabric, but honestly, space is space. That's a 3D space, and I said you need to take into account relativity. Relativity is actually, let me talk about that a bit before I go to that. It's a pretty natural concept. Imagine that we would have things traveling at an infinite speed. Imagine a billiard ball or whatever, or a planet. It travels at infinite speed. That means we would have no idea where it is at any point in time. It would be everywhere and nowhere at the same time. So that's a nonsensical concept. It's a mathematical concept, but there is a speed limit, I would say. And there's a few other very natural arguments you can build around, but the idea that there's a limit on speed, and that it must be the speed of light, which you define as something that has no resonance. What speed will it travel? Well, like a photon. Well, it will travel at the speed of a photon. It will travel at the speed of light. So speed of light is sort of a constant that is out there, and then you can use, you know, different natural units, and, you know, regardless of the value. But for me, it's something very natural, and it's then linked to, you know, the idea of time. Time must travel. You know, what are we doing basically a lot in physics, and we're actually looking at motion, something that moves. So how do you do that? You're gonna define its position in space, and you're going to define its, you know, where it is in space at some point in time. So if you would allow time to go backward, if you allow for that mathematical possibility, you know, you have a huge metaphysical or philosophical problem, in the sense that, you know, you see that red curve there. There we have a particle that moves back in time, and then it moves forward in time again, and then backwards again. And so basically what you see is that you don't have a well-defined function. You have a particle that at the same point in time, look at the beginning of that curve, at some point in time t, is not at a specific position, because it has been there at point t1, it has been there at point t2, and it has been there at point t3. And so you really have sort of a spaghetti curve, and you cannot do anything with that. So for me, the definition of time moving in one direction only is something that is, it's a mental or philosophical, or it's really like Kant said, it's a category of the mind. While the green curve there, that's sort of like, you know, it's something that moves in time forward. It can go back to where it came from, which is what it's doing on that graph. You know, it accelerates, then it decelerates, and it reverses direction. That's the graph there, the x is xt. It reverses direction, and it goes back to the same point in time where it was a while ago. But you see, we have a well-defined, well-behaved function there. And for every value of time, we have one and only one value of x. The reverse is not true, it's a function. So for one value of x, we can have you know, a number of times t1, t2, t3 where it was. So function is yeah, what you've learned really in elementary school. It needs to be well behaved, and so the domain and the what is it, the range of the function needs to obey that rule, where, you know, my time variable goes in one direction only. So it's like the thing, like, of course we can play a movie backwards, but we will always somehow notice that this is not a real movie. It's a real movie being played backwards. It does not describe anything real. You know, like two like charges, say two electrons or two protons that attract each other, or you know, yeah, this is wrong here. You know, it would be opposite charges that attract each other rather than repel each other. Yeah, okay, I see what I want to do here. You know, in the norm, when you play the movie, you would see two electrons would repel each other, and then if you play the movie backwards, you would see those two electrons would attract each other. That's what the image would show, and you would therefore know this is a movie which is being played backwards. It's not reality. We cannot really reverse time, and same goes for gravity. You know, something falls down, it doesn't go up again. So this is something where I want to couple it to, because people often say, like, well, you know, these Feynman diagrams and this and that. So what do you think about it? I think they're useful, of course. You know, coupling constants and making sense of very complicated situations. But there's something wrong there all in that convention where, you know, we say like, you know, antimatter particles, we'll just put them on those diagrams as particles that travel back in time. Mathematically, that's correct, because if you reverse the charge of something, you know, you will reverse its spin. So you put a minus sign in the wave function, but that minus sign applies not to time, it applies to the spin direction. And that's where I will talk about that. I feel that a lot of you know, weird stuff when you look at these wave equations, wave functions, and then you start adding and calculate probabilities and all these kind of things, is basically because, you know, people don't use their conventions in the way they should be using, and they should carefully think about what plus and minus signs in front of a certain variable actually mean. And that's also something what I have against using, you know, natural units too much. A lot of the people, they go for natural units. and there's different systems, and they say, oh, what, you know, when we use natural units, we get a Planck length, 10 to the power minus 35. So there must be something real. Well, no. Why should that be something real? Why should we attach anything? You know, because I can give you another system of natural units, and we'll get another natural unit of time or of distance out of it, and then, you know, it doesn't make it any more real. And furthermore, it hides the physical dimensions. Like if you equate c to 1, you know, c pops up in a lot of equations. You don't really properly distinguish anymore between c square and c, and then, you know, when you do a simple dimensional check on your formula, then you know, it will not point out any errors. And often these errors, you know, when you do dimensional analysis on your formulas, on your theory, you know, you see like, hey man, your physical dimensions don't make sense. So that's where yeah, I point that out because I will go into my modeling the plus or minus sign of the argument of a wave function. That really gives us the spin direction of a particle, and it's got nothing to do with time going in this or that direction. And it is convention. I could use another convention, but that's where I often use Occam's razor. Now look at all these things that enter into the argument of the wave function, the sign in front of the wave function, and just try to assign a meaning to that. Is the particle going in this or that direction? From what angle are you looking? Are you looking in the direction of motion or against the direction of motion? Do you have the conventions for your reference frame right? Is it a right-handed reference frame? You need to have those right, because the electromagnetic force is what I call a right-handed force. We know the magnetic force is sort of right-handed. The magnetic vector lags the electric vector. So all that stuff is actually in those wave equations, but people don't know it anymore or never knew it. And if you don't pay attention to these things, you really quickly get lost, and you try to reduce things, and you see simplifications that are actually not there. You make serious thinking errors in your thinking. So yeah, here I'm gonna have like 2 or 3 slides that basically, you know, are gonna tell you how I think about what wave functions are. Wave functions represent real particles, and we have 2 types of them. We have light-like particles, photons and neutrinos, and then we have matter particles. What's the difference between both is very fundamental. The math looks very much the same. Well, not very much, but at least, you know, we have the Planck-Einstein relation and energy mass equivalence. And also for wave functions, I'm showing that in the middle there, we can use a wave function to represent an electric field vector that we would associate with the electromagnetic wave. And hence we would associate it with the photon, because that wave is quantized. And so we can use a wave function effectively to represent that electric field vector, but something very different than using the wave function to model, I will argue that in a moment, you know, the charge inside of particles. That's a position vector. And so the wave function does have a physical dimension, and it depends on what you're modeling exactly. Is it a photon? Is it an electron, or is it a photon-electron interaction, like quantum scattering, elastic or inelastic scattering? Sort of how is that handshake happening between the two? You know, photon gets sort of absorbed by an electron apparently, and then, you know, that extra energy or angular momentum gets kicked out again in the form of another photon with a lower frequency, and then some kind of kinetic energy gets absorbed by the electron, so that moves then in a certain direction. So you really need to keep track of these physical dimensions to explain what is happening. So here is the photon, and I'll give you my photon model, because that's another thing that came up in the discussion with the man who had quoted me a lot in his book, but said, you know, in the end everything is photons, you know, and you should agree, because, you know, your electron model, you know, you have like a a model of an electron with a point-like charge inside, and it jitters around or moves around, and you know it moves. It has no rest mass, so I'll talk about that. So it's like photon-like. It moves at the speed of light. No, it's a charge. It's not a photon. My Zitterbewegung charge is not a photon. It's not a. It's something different, and people should appreciate that. But so here we're still with a photon. Here you sort of see like what you see here is a left-handed and a right-handed circularly polarized wave, and so in one you see what is the electric field vector. You should imagine there's like a magnetic field vector also, and its magnitude is 1 divided by the light speed c. So that's also something that people don't often get. Like we think about the electric field factor because supposedly it's much bigger than the magnetic field, but at smaller scales, and especially when you have, you know, the idea or sort of a model where you have a point-like charge moving at speed of light, whatever, then a magnetic field vector at that small scale becomes as important, or becomes actually the only thing that's important. So electric and magnetic field vectors, they also depend on your frame of reference. So that's also where it's useful to think like more in terms of scalar and vector potential, you know, invariant four vector equations. But so here I have that intuitive thing. We have an electric field vector going, you know, counterclockwise and then clockwise. Again, that convention depends on whether or not you're looking in the direction of motion or against the direction of motion. So always make sure when you try to model in a wave function that you make it clear which convention you're using. I'm looking in the direction of motion or against direction, because otherwise, you know, you really get lost in when you think about symmetries and whatever. So I think of a photon as really a point-like. It has its integrity, which is given by the Planck-Einstein relationship. The energy of a photon is Planck's quantum of action times the frequency of that photon. I put that somewhere here. Maybe not, I'll go into it. You can also write it as the Broglie relationship, because a photon has sort of a, you know, momentum, and that's related actually to the magnetic field. And so, yeah, we have a photon. It's people think, you know, how long is the photon? Well, that question I can't really answer. For me, it has no length. You know, it travels at the speed of light anyway, so just relativity tells us that, you know, its length will be 0. You have length contraction and time dilation and whatever. But there's a more fundamental reason, is that you know, a photon is really like a traveling electromagnetic field, and that value of that electromagnetic field is 0, except where the photon happens to be at some point in time. So for every position in space x, and for every point in time t, the value is 0 except where the photon is. So it's really point-like, and there are some experiments that say, okay, it should have a certain size, and maybe photons can interfere, you know, but they can be at the same place, and then they, you know, they double their energy, and but you know, can photons like be in some kind of collision? Probably yes, but essentially a photon is really point-like, and that's where, again, that wave function that I put there in the middle, I mean that electric field vector, you know, I model it. It has an x component, a component along the x-axis, and it has a component along the y-axis. And I said the E, it's not energy for, it's often very confusing. Energy E is not written in italics, as in normal typeface, capital. The E in italics, EX and EY, that's electric field. That's not energy. So, but in any case, the electric field vector is, you know, we can write it as an X component and the sum of an X component and a Y component. And then we know photons actually, you know, where did they come from? Well, they go from an electron goes from a higher energy state in an atom or a molecular orbital to a lower energy state, and I write a formula here. You have the Rydberg constant, and the energy of a photon is given by what I write here, the energy level N2 minus the energy level at the orbital N1. And then you can write it in terms of the fine structure constant squared times the energy divided by 2. I give an example: transition from the second electron orbital to the first electron orbital in a hydrogen atom. So the 1 over n1 squared minus 1 over n2 squared becomes 1 over 1 squared minus 1 over 2 squared is 0.75. We get a photon energy of about 10.2 electron volt. To make that a bit more real, that's ultraviolet light, so that's what we use to disinfect water. It doesn't penetrate very far, but it kills stuff that you want to see killed, like bacteria. For us it's not dangerous, but for the bad stuff that's in water it is dangerous, and kills it. So we can then calculate a cycle time, because all these so the cycle time is 0.4 times 10 exponent minus 15 seconds. We can calculate wavelength, 122 nanometer. The interesting thing is also, you know, that's sort of what I call a one cycle photon model. It's a cycle. Yes, because as it travels through space, it has that wavelength where the electric field vector, you know, after a certain time, its cycle time, and after having traveled during that cycle time a certain length in space, the electric field vector and the magnetic field vector that comes with it will be in exactly the same position. Same angle, same phase, same magnitude, everything. And so then you can calculate that. This is a formula I have from my manuscript. I published something on that. You can also see it. It's sort of, we don't have a charge because, you know, to calculate a field strength, the fundamental equation there is the force is the charge times the field strength. So the field strength is the force divided by the charge. But I told you, this is a photon. There is no charge, so there is no force. If there's nothing to act on, you know, we only have a field. But you know, combining equations, you can just calculate sort of a radius vector, which I don't do here, but I can calculate a field strength. Well, that's actually sort of the radius, the magnitude, so many newtons per coulomb. But it's not, as you can see, a physical radius. You know, if you shoot something at this photon, another photon, for example, you know, it will just go straight past, because the photon is really point-like. I put two other things here, which are very, very important. One is a fundamental mistake I found in the way quantum mechanics is being taught. I followed an EDX course and refinement, and I always said it like, you know, when you simplify and go for solutions and wave equation and this and that, you basically treat the phase factor plus pi and minus pi as the same, because you know, Euler's number at the exponent plus e, the imaginary unit, times p, you know, that's minus 1. You know, you rotate, think of rotating the vector plus 1, or that position in two-dimensional space, you know, following the direction of the imaginary unit, which, you know, the imaginary unit is like a rotation operator, and so it's defined conventionally, mathematically, as a rotation which is counterclockwise. So you arrive at minus 1. Now, in contrast, if you have minus p and e to the power minus, you also arrive at minus 1. So in mathematical equations, you know, you will say, oh, that's a phase factor. You know, in a wave function, we can add these phase factors and you know, cancel them out one against each other. No, it matters how you get from plus 1 to minus 1. Either we go in the positive direction, counterclockwise, or we go in the negative direction of the imaginary unit, and that's a huge mistake. And that is made in quantum physics, is that, you know, physically, it's what I write there. E with an exponent plus, it's 2p. 2p is a full cycle, be it for describing, you know, motion or orbital motion or linear motion. The only time you can cancel something is when you have an extra phase factor of 2 pi. And even then, you need to be careful, like, you know, as if we're modeling some interaction, are the two particles at the same position? Because if they're not, then you're not modeling an interaction at the same time and at the same position. And then the other thing I put there, the dynamics of the electric and magnetic field vector. This is to illustrate what I'm gonna talk about when I talk about dark matter. So the magnetic force is electromagnetic force is a right-handed force. The magnetic field vector lags the electric field vector, and I always wondered, like, I mean, two things. One is you know, we model the electric field vector and we think we're done, which is correct. But you should not forget about that thing. And I always wonder, like, maybe in nature it is like a bit when Dirac wrote down his wave equation for electrons. He saw, like, wow, you know, this thing would work for a positive charge as well. And so maybe positive electrons exist, positrons, and then they were discovered. And so I have got something like you know, when dark matter was discovered, and actually, you know, we see dark matter doesn't send out any radiation we can capture. It doesn't seem to interact. We don't see supernovas or stuff happening with dark matter, but we know it's there because there's gravitational effects that we can see, you know, galaxies that spin too quickly or slowly, there's stuff around the cosmological constant. We know there must be a lot of dark matter out there, and so why can't we see it? Why doesn't it interact? Why doesn't, if it sends out the radiation, why don't we capture it? I think it sends out the radiation. Same things must be happening. But I always thought that maybe in nature somewhere, you know, we could have a left-handed magnetic force, and I think it's a hypothesis. If it's an interesting one. Maybe in 10 or 20 years from now, we'll know this is a nonsensical hypothesis or maybe a sensical one. But think of these things. Always think about you know, what are the sort of degrees of freedom in you know, a mathematical description, a plus or a minus sign, all the various symbols you use, their dimensions, and sort of how is the geometry, and is it possible maybe to find some, you know, the Occam's razor. Occam was a philosopher in the early medieval times. Like, if you have a good description, a good theory, you know, the degrees of freedom in your description, in your formulas, in your model, they must sort of match the degrees of freedom that you have in your system. So, and that was something until the discovery of dark matter, which I thought, like, okay, we maybe there is an anti-force. Theoretically, we could have one. But I'm digressing. The difference, maybe before I continue, between a photon, so that gets emitted by an electron that goes from one energy state to another. Neutrinos are clearly, you know, they get emitted and absorbed by nuclear reactions. I think the nuclear force, you know, what keeps a proton together and what a proton actually is, it is essentially, you know, an oscillation with a different structure, and I will talk about that. We will talk about the structure really of electron protons. That's something after the Second World War, you know, you have a huge discrepancy between, you know, these models, quark, gluon, you know, everybody thinks in terms of point-like subatomic particles, point-like, but really in the sense like they have zero dimension, but then you load a lot of properties on them, like, you know, strangeness, baryon number, what have you. But, you know, if they have no dimension whatsoever, then how can they exist? And then the other thing is, like, we know from experiments that electrons have a radius, you know, electron radius, quantum radius. We measured that scattering radius since in the 20s and 30s, and then, you know, theoretical physicists sort of forgot about that. So I think very much, and I'll go to that now, in terms of matter particles, that they have a structure, and that their scattering radius and their magnetic moment can be explained by, you know, what characterizes matter, and it is that there's charge inside. I think very much in terms of a sort of a ring current model, which I will explain. But so that's the photon model: no charge, a really point-like, a quantized electromagnetic field traveling in space and in time. Here I go. I reiterate, you know, this is a bit the electron model. You have the black thing there. That's a ring current. That's the electron, I would say, in when it's not moving. it is in our its frame of reference and our inertial our frame of reference, the inertial frame of reference, it's the same for the electron as for us. So we're both in one frame of reference. There's no motion. And so then you can calculate and say, like, here I go back to a hypothesis of Schrödinger, who actually discovered that Dirac's wave equation had a very simple solution. He said, you can just sort of have like, there must be some kind of local oscillatory motion, with charge that moves at the speed of light in a small thing, and that makes your wave equation. It's a very trivial solution, and that's how we think of an electron, as some kind of ring current. And it works out because you have Planck-Einstein's relation. Then you think like, okay, what is the energy? What is the mass of that thing? Well, it's just that charge in motion. So and then the frequency, instead of thinking of a linear frequency, that's the mistake that Louis de Broglie made, I think. He saw that matter particles, there's something with the frequency there and the wave function, and what kind of frequency is it? And so he interpreted it as a linear frequency, some kind of linear frequency. And I'm going like, well, it could be something that goes around and around, and you have an orbital frequency, and that sort of works out a lot better than thinking in terms of a linear frequency, because then you have to explain, like, what is it, and you arrive at wave packets with slightly different linear wavelengths, and these dissipate, and it's a lot of trouble, and it never got clearly explained. I think my model here is clear. So it's based on very classical physics, and most importantly on de Broglie's vision of what a matter wave, what matter particles are. And then I have that c is the radius of that oscillation times the frequency. That's just the formula for an orbital velocity. I said we think of a point-like charge, but not really point-like in the sense that you think of quarks, gluons, no dimension whatsoever. We think the classical electron radius has a radius, because that explains then the anomaly in the electromagnetic moment. But so you get the radius out, the real scattering radius, the charge radius of an electron. And the interesting thing is that it makes sense in the wave function, because there I write that when we think of that point-like charge moving also linearly, that's sort of the bluish and brownish and reddish trajectory. If it moves at the speed of light, then the amplitude of that motion, the radius of that circle, black circle, must diminish, because some of the velocity is now linear rather than orbital. And so the radius of that thing must become smaller, and there is also time dilation, in the sense that the frequency will become less. And so it's a beautiful diagram. I borrow it from Di Tommaso and Vassallo, two Italian researchers who work on low energy nuclear reactions, and they believe sort of in a Zitterbewegung model, or a ring current model, which is actually more than 100 years old. It was in the 1920s, I think, that a British chemist came up with it. I can't remember his name. For the moment, we'll come back. But they use that model, and they say, like, look, that's how an electron looks like when it starts moving in space. And then sort of in the wave function, its argument, so the wave function is a, the amplitude, times e Euler's number to the exponent e, and then times the phase. The phase. What is the phase of matter? Well, the phase is a there is that delta is 1 over h times the energy times the time minus the linear momentum x. And I won't go too much into detail, because I will get lost here, and I'm already like talking 50 minutes, and there's still some slides to come. But you can show that you can break down that argument that for now was very mysterious. What is it? What is the frequency? This is how you can decompose it. And a relativistic energy, so it depends on the velocity, the linear velocity of the electron, a linear momentum times x, and then you apply Lorentz transformations as in as that, and you can always, that's the good thing you can show, you can always rewrite it in terms of your initial rest energy of your electron, so many electron volts divided by just Planck's constant, and then the T, I always forget sort of T accent. The time as measured in its own frame of reference, in the rest frame of reference of the electron itself. This thing shows really how length contraction, because you see that radius comes down, so the electron becomes like smaller from our point of view, but of course not in the reference frame of the electron itself. But from our point of view, when there's linear motion being added to that orbital motion, yeah, for us that radius of the orbital motion becomes smaller. Things happen with the frequency, which means with the time. So the electron moves faster and faster, and theoretically we cannot accelerate it again to the speed of light. That would because there is a rest mass, unlike a photon. The electron has a rest mass. It is in that oscillation of the point-like charge. So we can never accelerate it to the speed of light, but we can, in our modern accelerators, applying tremendous amounts of, energy and magnetic fields, and accelerate them close to the speed of light. Then it looks to us that that thing is becoming smaller, and also that time is going smaller. That's also where unstable particles, when they get accelerated, they live longer, because they, in their frame of reference, time, which is measured, I would say, by their own clock, the frequency of motion of that point-like charge inside, or two, think of a neutral, like think of two charges inside, a positive and negative one. Their clock speed goes lower, becomes smaller. Okay, next slide. Here I'm going to the proton model, and at the same time, because you may have thought, whoa, this is just total nonsense and this and that. I'm really going back to Louis de Bruij's original thesis from 1924, which got published in 1925 in the Annalen der Physik. This is what he originally wrote, because often people see that the relations of de Broglie, h times the frequency is the energy, but this is what he wrote. He wrote it in terms of the rest frame. He said, maybe because of some grand law of nature, we should think of matter particles as being like energy packets, and energy implies motion, so we should associate perhaps a periodic phenomenon. What it is, that's what I'm telling you. It's I interpret it as the orbital motion, but we should associate sort of that frequency nu 0. This is not a v, this is a nu, a Greek letter, with an energy packet of a rest mass m0. So that's a particle, to be clear. So that frequency, then we should measure that in the rest frame of the energy packet, and then we can do relativistic transformations on it, which is what he does in his thesis. But that's what he originally said, and I believe it's fully correct. We need to think of matter particles as basically a charge oscillation, and that oscillation is not linear. So don't think in terms of wavelengths, think in terms of a radius vector. The time that is needed for that point-like charge to go around, to move around in one cycle. The motion could be regular or irregular. It must be regular enough because we can measure those frequencies, and there's a lot of experiments and that show that frequency matters, and the wave function, this and that. It must be very regular. So I think it's just plain circular motion. I have a model for the proton as well, and that's a bit special. But before I explain that, you see what I put there is at the bottom, I like that one, is a radial engine. It's like a classical star engine of an airplane. But it's a bit the same thing. You have a ring current. You can analyze it as an oscillation, as a sum of oscillations, in the x direction, the y direction, but you can also model it as sort of 6 or 8 or 10 or an infinite number of pistons, really, or oscillations, which each pack like half or a fourth, depending on the number of cylinders you have, and it creates orbital motion. I like that metaphor as well because it also shows like these blades, and the blade story is not directly, the propeller blades, directly related to that idea, that metaphor of linear motion turning into orbital motion. Because really, orbital motion, you can see it as the sum of a vertical and a horizontal oscillation in one plane. And I'll come back to the proton. There, you need to have the third dimension. But the propeller blade is an interesting metaphor as well, because it explains, like, quantum tunneling. We have these potential walls that are like static things, and people go like, how can you tunnel through them? The kinetic energy of the particle, or the energy of the photon, is lower than, let's talk about the charge, is lower than that potential wall, so it shouldn't go through it. But it's like, when you think in terms of particles being charged oscillations, then, you'll have like sub-Planck or oscillations that it's like a wall or propeller blades that go round and round and round. If you shoot bullets at it, well, you can be lucky or unlucky, depending if you're the enemy of that plane or not. Your bullet can hit the propeller blade, but it can also hit the empty space in between, and so that moves around. And it's also like when velocities get really high, it becomes kind of difficult to say like, we do not know the initial conditions of the system where the blade started rotating, so we actually don't know where the blade is, where the propeller is. We just know that it has a certain probability to be somewhere at a certain point in time. Or in a certain space, and then of course you need to normalize to see how big is that space, but that's really the essence of probabilities and potential walls. Think of those rotating propeller blades where we have something that is moving at a very high velocity, and because we don't know the initial conditions of the system, we don't know exactly where it is at exactly what point of time, but it's somewhere. So it is statistically a deterministic system. But yeah, it's statistics. We work with probabilities because we can never actually point out, we don't know the initial conditions of the system. So that point like charge also it is somewhere at some point in time. The motion is regular, and that's where these probabilities then are based on. So for the proton, you should do something here that is kind of creative. But it should be feasible. If you have, I said, an orbital motion, right? And we look at it as the sum of some thing going left and right and some going up and down, okay? It's within one plane. Now we can imagine a secondary rotation of the plane itself, and that's what I show in the upper hand corner, where you have this is something showing 720 degree symmetries, Dirac's belt trick, or the Balinese cup trick, or whatever you want to call it. But it's sort of that mystical thing, like, oh, matter particles have a 720 degree. Well, think of a rotation within a rotation, with a different frequency or the same frequency, but it may return to its original starting position only after both the rotation in one plane and the rotation in the second plane have made the full have gone through the full cycle. And so these rotations in 3 dimension, one planar, like what you have for the electron, for the proton, and that fits sort of with nuclear packing models of neutrons and protons, they do appear to be spherical. So yeah, if you think of sort of an oscillation in 3 dimensions, x, y, z, or 2 planar dimensions, you know how it goes. Basically, you have your x-axis, you make a rotation. So you have then a plane, and then you make a second rotation, and then, well, you have your 3D space, you have a sphere, right? So that's the model, really, that we have an oscillation in 3 dimensions. 2 rotations, 3 dimensions. 1 rotation is 2 dimensions, but say 2 dimensions, again, 2 linear associations. So counting the number of oscillations depends on your definition of an oscillation. If you talk a linear one, an electron is a 2-dimensional oscillation. It's a plane. If you talk about a planar, an orbital, then there's just one orbital frequency in an electron. In a proton, we have 2, and we have 2 planes, and an oscillation along the x-axis and the y-axis and the z-axis. So the Einstein's mass equivalence relation and Planck-Einstein relation that you have there, which I apply to like a freak an electron. The energy of an electron is its frequency times Planck's quantum of action. For a photon, I put it there, gamma. So that's quite obvious. In the middle, we have it there for a proton. There we need to think like the energy of in the oscillation. We can apply the energy equipartition theorem, where we say like, okay, half of the energy is going to be in one oscillation and the other half of the energy is going to be in the other. And then, you know, the formulas get a little bit more complex, but not very complex. So, you know, so the energy in an oscillation is proportional to the square of the amplitude and proportional to the square of the frequency. So I could put a formula here. I did that in my last presentation based on, you know, it's very simple. The energy is, you know, the coefficient, the radius, the amplitude squared times the frequency squared, and then I get my proton radius, which I put here, 0.84. That's being measured. Depends a bit on the period of measurement. But here I do it actually on the magnetic moment, because it's the same thing. You know, if your model is consistent, you should be able to derive from these formulas the magnetic moment, which we know particles have. They have a magnetic moment. They will align themselves when they go through, you know, an accelerator. We can keep them in, we can store them based on the fact that they have a magnetic moment. The ring current is like a little magnet, and you can keep that in place. So the proton has that. It's a much weaker magnetic moment than an electron. But all these things, like, you know, thinking of a proton and an electron as, you know, a moving point like charge, a ring current which has a magnetic field, and then, you know, it is an oscillation. But what is the oscillation? Basically, Maxwell's equations work. It's a quantized magnetic field, and it's just the right size. You know, the radius and the ring current that is there is just like the right size to keep, you know, the charge also in place. The one thing you have, and that's the big mystery, is there's like a bit of a fine-tuning problem. It's like a superconducting current, but with the difference that you go like, well, if I have a superconducting current, I have a wire that keeps the basically a charged pair in place, because we talk Cooper pairs in superconducting currents, you know, these things that you've seen on videos, and macro quantum mechanics, I would say. The ring current, you know, it oscillates in space there, and so you go like a little bit, there's nothing to keep it in place. For me, that's not a philosophical problem, because the Planck-Einstein relation gives me like that equation, which I don't, you understand it and you don't fully understand. It packs exactly 1 unit of h or h bar, depending if you use. So, and that's it. It can that's the particle. It's defined the integrity of the particle by the Planck-Einstein relationship. Energy is Planck's quantum of action times the frequency, or h bar times, you know, an angular or an orbital frequency. So that equation explains and sort of solves the fine-tuning problem, as I would call it. Like you say, well, if we're going to disturb that, a little motion of the point like charge, you know, everything falls apart. You know, it's superconducting current without a wire to hold it. For me, that's a philosophical problem, and it's not. For me, it's not. The Planck-Einstein relation is there, and that's where you go. The wave function for a proton, then, because I said an electron, we can use the wave function, Euler's number, and then a complex exponential to model the position vector. I do that in papers, and I also sort of go through the mechanics and the mathematics of it to say like, okay, when we take, if it has a position vector, that wave function, sorry, the derivative in regard to the position, you know, should give in regard to time, should give a velocity, and then I arrive, you know, at c. So the model works, and then, you know, I get an acceleration vector, which is all these kinds. So the model is sort of really self-consistent in terms of both, you know, Maxwell's equations. It is sort of like a perpetuum mobile, an electromagnetic perpetuum mobile, but it also makes sense in terms of, you know, physical dimensions, derivatives you do on them to, you know, calculate other quantities and all that kind of stuff. The thing is, for the proton, you get a rather special one, because I said we have I as an imaginary unit, and we need a second one, J. And here again, you need to make sure that you have your conventions right, that you also lose like like a coordinate frame, a right-handed coordinated frame, and then you say like my J vector, my J, not a vector, rotation operator, is going to be right-handed and you see you need a lot of convention to sort of say like, okay, now I see this proton is moving in that direction. That oscillation is in that plane, that one is in that plane, and then the plus and minus signs, they're going to measure the spin of the two oscillations. So that's a much more complex chirality, I would say, than just spin, plus or minus, up or down. For a proton, it's a bit more complicated, and that's also something where I think like these things of symmetry breaking or spin or whatever, it's too abstract. Make it specific. But you get that formula. And you get a radius of a proton that the proton radius puzzle is declared solved. They measured it precisely, and this is the theoretical explanation. I shared it with a PRAT project in JLab and with Dr. Paul, and they say, oh, this is a bit numerology, too simple. Maybe you should apply I don't know what. Gaspar talked about lattice theory, and I'm going, no, this model works fine. But you have a 4 factor there instead of the radius is equal to h bar divided by mc. That factor 4 is there, and it's got to do with these with the 2 dimensions, the fact that the energy is in 2 planar oscillations. But it's the same factor 4 that you have in the formula, the surface formula for surface of a sphere is 4 times pi times r square. That's the formula for the area of a surface, while the area of a circle is just pi times r square. So that factor 4 is just the same factor. There's no mystery in there, and it all sort of fits together. Okay, we're at 1 hour. I'm gonna continue. You may take a break. Maybe I should take one, but I'm gonna continue. Here I want to go back, sort of, I told you these are my models, right? My photon model, my electron model, my proton model, matter particles, they're charged. It becomes complicated. I try to like model a neutron. A neutron, I think, it's not stable outside of the nucleus. So that tells me it's not a fundamental particle in the sense. It's sort of like a glue inside of the nucleus that holds actually protons together, because so the neutron as a neutral particle is probably like some positive or negative charge in, because it has the same size as a proton. So we also think of some kind of 3-dimensional oscillations, but we've got like a 2-body problem, kind of difficult to calculate. And on top of that, it will have some spin coupling or coupling of the chirality with the protons that surround the neutron, because as soon as you have 2 protons, you have a neutron. There's no nucleus with only 2 protons. So protons they repel each other, and they need some kind of glue. And I look at the neutron as a glue, not as a gluon, but as some kind of glue particle that is needed, a composite particle, let's say, that is stable inside of the nucleus because it's part of the nucleon system. Be it in hydrogen or more complicated nuclei. But the thing, so I explained that particle model, and she said neutrons, and going to more complicated things, you really get a bit stuck there, because a 2-body problem you can analyze. A 3-body problem, that in physics is actually analytically very difficult, impossible to solve. Mathematicians, I don't know the proof exactly, but they've shown that like as soon as you have like 3 charges, there's no analytical solution. So there you need to fall back on some kind of model, numerical model. So that becomes very difficult to complicate and to model. But an electron model, proton model, photon model, and a neutron model, this easy. And I've got those, and you can read my papers, and it's there and explains, all the physical properties of. And then a photon neutrino. That's the thing with the neutrino. Think of a neutrino also, because it comes, an excited proton, whatever you want to, or something that happens in the nucleus. And I said we're talking 3-dimensional oscillations there. Think of a field oscillation, not like that electromagnetic wave, or like that electromagnetic wave, but add a 3rd dimension to it, and then you have, an oscillation in 3 dimensions that moves through space. And that's what I think a neutrino is. There's no charge there. It may have some rest mass, or it may not fully travel at the speed of light, because I said that the oscillation in the length in the direction of motion, will give it some kind of, energy in that direction, and therefore some kind of rest mass. But to go back, so I've explained my models. Here I'm talking about interactions. You see a little picture of Compton scattering here. A photon that arrives, hits an electron, and then after a very small time, the electron ejects that photon again. Well, it's a different photon, I think, because it has a different frequency. The difference between energies gets translated. The electron was at rest, now it has a certain direction, and all these things, these models fit, and they're not, this is not uncertainty. The photon has a certain direction, a certain energy, the electron is at rest, and what comes out of there, okay, the direction, that angle where the photon gets ejected and where it goes out, that is sort of, that has to do with these initial conditions that we don't know, sort of that handshake between the photon and the electron, the point-like charge, the alignment that happens there. But once you've got one variable of that system, that delta angle or direction in which the free electron is moving after the collision or absorption and emission of the photon, that's all can all be calculated. And so that's where I put at the bottom here my model is that if you take care your wave functions and you apply your conventions really well, then you can model spin up or down. You need to sort of say, okay, this particle moves in the positive direction or the negative direction, and your wave function will look different, and you will use actually all these degrees of freedom, a plus or a minus sign, as you can see there. And then that's where there's no magic anymore between, we'll take the what is the complement of a wave function, and then you arrive at a positron or whatever. So the antimatter we can model as well. I argue that if you define your conventions really well here in this model, and then it's what I say, like, okay, you can think mathematically, describe it by a minus sign in the exponent, but putting a plus or a minus sign in front of the wave function will actually model antimatter. I will not go into detail of this thing, but it's sort of really very complete. For every way you can write the wave function with a positive or a negative coefficient a, with a minus kx and a plus omega t, or a minus in front of the imaginary unit, and then you got 4 mathematical possibilities for a positive coefficient a, and that will model all of your normal matter particles. And if you put a minus sign in front of these, plus, then you will have a wave function that adequately describes antimatter. So here we've used, and that's where I was happy with my dark matter theory, is we've used all the degrees of freedom in sort of wave function math, and I will show a few more equations, except that we implicit in all these things are, as said, we model for photons the electric field vector. For matter particles, our wave function will describe really the position vector where that point-like charge is, and so we've got a complete description for each physical situation, and then how we combine the wave function of a photon. I had an old professor said, Sean, we forget the wave function. Photons don't have any wave function, just that electric field vector. It's kind of neat, you can describe it mathematically with a wave function, but photons don't have wave functions. I agree, not agree. I mean, I said mathematically it's kind of nice when you can describe quantum scattering in terms of a mathematical model. But indeed, you cannot just combine that wave function I showed you from a photon with the wave function because it's two different beasts. The one wave function is a position vector, basically a rotating position vector in 2 or 3 dimensions, and for a photon it's an electromagnetic field vector. So the way you're going to model the handshake between those two things, the interaction, the coupling that happens, all these kind of things, that's going to be a different beast as well. But I put that Feynman diagram there again because I said that confuses a bit. That sort of shows a sloppiness in using wave function math for modeling very complex situations. The thing we do not have in this thing is that still, you know, we forget about the magnetic field, and we forget there's a hierarchy in there, that the magnetic field vector lags the electric field vector. And I put Maxwell's equations there. This is also something I wanted to point out. You know, Maxwell's equations are correct. They describe everything of classical physics. The thing is, why don't they work or seem to work? They actually do work, I said, for a ring current model. We can apply these. Is, you see, Maxwell's equations are written in terms of charge densities. That rho that you have in in these equations, the curl and Laplacian operator there on the operating on the electric field. It's rho divided by, you know, the electric constant, and so you have Gauss law, Faraday's. But yeah, when you arrive at the elementary particle level, you're really talking not about the charge density. You're really talking about the charge. It's here, and so it's moving, you know, at an incredibly small scale. And that's where Maxwell's equations break down, and they don't break down at small level, because you're no longer thinking in terms of charge densities. It's like, oh, that plane also, where's the charge? Well, it's somewhere, but its speed is so high, so it works, but you need to think about how do you define charge density when you're talking, you know, elementary particles at these scales. What does your concept of charge density translate into? It's no longer a static concept of, you know, charge in space over a surface and some kind of average. No, that charge is somewhere at some point in time. We just don't know because of its high speed, and we don't know the initial conditions of the system where it is. So you have a very different logic that comes up there, but you still have the basic thing, you know, when there's no charge involved. What I put there, the curl of the electric and the curl of the magnetic field vector, these are the only two equations that are left over when you sort of say, well, there is no charge, so there is no charge density. So these are then the only two equations that matter. You still have in the signs, you know, the curl of E is minus the time rate of change of your magnetic field vector, and the curl of B is plus 1 over c square, and we know magnetic and the electric and magnetic constants are equal to 1 over c square, so they're clearly one and the same phenomenon. But so if you would write that in wave or in my rotation or quaternion, or whatever you want to call it, in imaginary or complex algebra, it's I have a force that is taking into account, defining all my convention, right? That electromagnetism is a right-handed force, that my coordinate frame is defined as being right-handed, that I look in the direction of travel of a wave or a particle, you know, then I can write, and that, you know, the imaginary unit E is a counterclockwise rotation. So then I must write my magnetic field vector as minus the imaginary, minus a rotation operator on E, and you go like, maybe, just maybe, with this big mystery of dark matter, could we have sort of an anti-force, a left-handed force? And I think it's the only explanation, because you're never going to get anywhere with sort of reinventing your quark-gluon model and then think, okay, now we need axions or some kind of special boson, and what generates the mass of dark matter and or its energy. It's going to be the same thing, you know. It's matter, but it's dark matter. So what can be different about it? Well, it must be the force inside, the force that makes up an electron, that makes up a proton. You know, for dark matter, that force is going to have a different, and I call that a different signature. Why do I call that a different signature? Because if you believe this model is maybe something that might work, it is like a signature. It's like you have also for interaction or interaction theory. No, dark matter is not going to interact with matter, because it's like a door and a lock, and if it's the electromagnetic force, you know, somehow when a photon meets an electron, you know, they're going to align or whatever, and these electric and magnetic field vectors are going to add up, or they, you know, interfere constructively or destructively. But for matter and dark matter, that's not going to happen. For matter and antimatter, yes, you know, they come together, matter and antimatter. The electric and magnetic field vectors, you know, they're going to line up, going to be opposite. And you can show that, you know, for the normal right-handed electromagnetic force, yeah, there's going to be complete destructive interference. The electric field vectors and the magnetic field vectors are just going to, you know, reduce to zero. And then where does the energy go? Well, it must go into some, yeah, into a gamma ray, a photon. What happens then to the charge itself, you might say, but that's a different beast. Or a different question to which I have no answer. You know, I look at these experiments and I sometimes go like, you know, you see pair, anti-pair, destruction, annihilation, creation. It always happens like around the nucleus. So maybe the charge comes from somewhere and gets ejected and goes somewhere. I don't know. It's high energy physics. But what I do know is that if you would assume, and I'll go to the next slide here, that we could have something like this, where we have a curl with a plus sign, a left-handed electromagnetic force, that, you know, your whole mathematics, what I put there, actually that first wave function, plus or minus, I said that's the matter-antimatter modeling you do, times plus or minus, that's your spin direction, the rest energy divided by h bar times t. I added here, it was just an idea. If we have unstable particles, maybe you can model them by putting in a transient, so that it's sort of an envelope function that reduces the oscillation. I don't think that's a good idea. I'm just showing there's a lot of possibilities in this math. Just to continue on that, I don't think it's a good idea because we do see that unstable particles, they break down at one point in time. It's not like they're like a transient oscillation that sort of fades out. But I'm just showing you all these conventions that we have with these plus or minus signs, which we effectively use in like Schrödinger's equation in free space, which I'm putting here. Yeah, I won't go into detail. Maybe it's interesting. The point like charge inside of a matter particle, you know, you think about, okay, it has no rest mass, but it moves around at the speed of light. So it must have a relativistic mass. What is it? It's very nice. It's the one, or it's half the total mass of the electron, and you can show that in relativistic or non-relativistic equation, oscillation, whatever. It's really nice, and it explains the that factor 2 that you have in Schrödinger's equation for a hydrogen atom, or like in this case, just plain propagation of an electron in a crystal or in free space. But that's a different matter. But in any case, all these equations that I put down, and where I say like, okay, all these wave function man, all these rotation operators, and you know, I said for a proton we can involve bit of quaternion math with 2, and then, you know, we can define k as the product of I and j, and it all works fine. But if we would have a left-handed electromagnetic force, you know, we can't reconcile this math with sort of the modeling we would do. It would be very similar. Huh? We would also have like a wave function math for dark matter, where you can say like, okay, dark matter particles, they must have a spin direction. And they go around, and the charge inside goes around, and this and that. And it's the same charge, a positive or negative charges. There's no such thing as a dark charge. No, it's just positive, negative charge. And there's no such thing as a dark spin or dark chirality. No, it spins in this or that direction. It's just like the force that makes it spin around, that keeps that little thing in place, is governed, I would say, by an animal that we don't know, a left-handed electromagnetic force. So it's like it made me think of Feynman has some excellent analysis of, you know, symmetries and asymmetries in nature, but it's like the one he doesn't analyze, where you can say like we can talk mirror symmetries and parity and spin, and I said more complicated chiral structures, rotations with a rotation, that we turn them inverse out, or we mirror them, and then we see like, okay, that symmetry gets broken. But and that's the thing also, where, you know, you go for that symmetry breaking, CPT symmetry, I won't go into too much detail, but you say like, hey, maybe it's that, maybe at some point in time in, like, you know, Cowan reactions, maybe at some point some particle is produced that is governed by a left-handed force. The symbolism you would need for it is completely it's different, and it's not different. I made a suggestion here, you know, I could put like a big overbar or an asterisk, or I don't know what. I just write down here a wave function which looks exactly the same as the one that we have for matter and antimatter. The plus and minus sign in front is for matter, antimatter. What's in the exponent is the spin direction. And then, of course, we have positive, negative charge. But it's captured by the matter-antimatter distinction. An electron and a positron, how do they differ? Their spin direction is reverse, or you can describe anything you want with that wave function, but if the matter particle would be governed by an anti-force, by a left-handed force, then we would sort of need to make it clear that this wave function we cannot combine with matter and antimatter wave function. That's why I put like a big reverse arrow on top of it, to say like warning, warning, different beast, different animal here, and do not mix it up with all the rest. The thing is, it's quite significant to think about this, because most matter in the universe apparently is antimatter. So I will take a little break because somebody is ringing the doorbell. Oh, by all means, just a second. I will resume in a moment. Okay, I'm back. I hope this worked actually, because I don't have too much experience with these videotaped presentations. I keep it very simple with PowerPoint and put the camera on and then I start talking. We're almost there, 1 hour 25 minutes into the presentation. I was wondering if I had, I actually gonna talk now about the main thing I wanted to talk about, and that's a bit this warning by, it's not a warning. I really enjoy people reacting and saying, hey Jean, you're really, your modeling is interesting, but can we go like one step further? You say everything is energy. I say, yeah, everything is energy. But then, energy filaments, quantized space, the vacuum properties, and I'm going like, no. Energy is a scientific concept, and we can model it. But for me, ultimately, it boils down to something that is in motion. It's a charge that is in motion. I don't have any other concept for the moment. How can we substitute charge for something deeper or more fundamental? I don't see how we could do that and why it would be useful. I'm gonna talk about that now. I just plain here because this is really, I think it's sort of, my daughter is also saying, Daddy, get out of it. You're thinking too much about these things. They keep you busy. But that's my paper on ResearchGate, an anti-force to explain dark matter. Please read it if you're interested in these topics, because I said it is for me, this is the most significant discovery of the 20th century, and the two teams who discovered it got a Nobel Prize for it, and I think it's really well deserved. I'm not convinced all Nobel Prizes are given to people who really sort of deserve it, and I'm talking a little bit about the discoverer of the Higgs particle, something that gives mass, a scalar particle. Of course, mass is a scalar quantity, and how does it then give mass? Or messenger particles that carry very linear momentum or energy up and down, virtual particles. Yeah, but our experiments indicate that, the theoretical models behind your experiments indicate that maybe your theory might be right, but you're not proving it. So as long as you're not proving it, it doesn't exist for me. But look at this one. I think it's one that experiments may be designed to prove it and to capture maybe dark radiation. I don't know how yet, but it should be measurable, because we're talking, if dark matter is basically like, our matter, then we're talking pretty, and I said, it's most of the energy and mass in the universe appears to be dark matter, based on those discoveries of astronomers and the way mass is distributed, and what it explains the accelerating pace of expansion of our universe. So there must be a lot of that mass around there, and so it's big. I think it has the same structure it must have as what we have. We don't need to reinvent a whole new framework like axions, and it's just like, we need to design experiments like they designed for measuring gravitational waves, where they also did, like, I think 15 or 20 years ago. Gravitational waves were predicted. They were difficult to measure, very fine, but they found them. Matter and antimatter, they merge in a big explosion, destruction of matter, and it changes the space-time structure, sort of, I would say, the gravitational field, and that change is transmitted as a wave, a gravitational wave, and they found it. I'm not going to talk about gravity because otherwise you will think I can somehow link electromagnetism to gravity, and I can't. For me, gravity is more of a, that's a different topic. And that's another reason why I'm saying, like, please don't come with grand unified theories on electromagnetism, gravity. I really don't believe them. These are two separate things. But an anti-force that could explain dark matter, well, the paper is there. Let me know what you think of the idea, and that is what I have to say about it. So maybe then on, yeah, what is reality? I said, look, really get rid of the idea that something that is relative, you know, I said time and distance itself in relativity theory, you know, your reference frame matters. You will measure time and a distance interval differently depending on your reference frame. Mass, force, energy, momentum, these are all relative concepts, but they are real. These are real measurements. And then you have a few absolute things that don't change, not depend on your frame of reference. The speed of light is a constant, always, no matter how you measure it, and your reference frame will not influence your measurement of the speed of light. Quantum of action is an absolute constant. The elementary charge, the electron charge is absolute. I would sort of add, because you know electrons and protons themselves are like some kind of their mass. Okay, that will depend how you measure it, but the electron and proton are the two things we find in terms of matter particles out there in the universe. So you might add them that it is something absolute, an electron and a proton. But these are the basic relative and absolute quantities. And you know, when you ask me what is reality, well, reality is a bunch of is the equations that I look at to, you know, make a representation in my head of what might be going on. So for electromagnetism, that's Maxwell's equations. For a hydrogen atom, the electron orbit Schrödinger's equation, or in free space we have one. There's a geometric interpretation of the Breuil's wavelength. For me, E is mc squared. It has no secrets. Everything is energy. You know, inertia is the inertia of energy, and energy is charge in motion. So mass is nothing. But at the same time, you know, it's real, of course, and especially at the macro scale. This is another thing. Maybe the one thing I'm going to say on gravity is. You have all these models that try to incorporate some kind of microgravity into particle modeling. And I'm thinking of a Russian scientist, Alexander Burinsky, who is further working on, you know, the Geon model of Wheeler, John Archibald Wheeler. I believe in mass without mass. This is the models you see. You know, mass is a measure of inertia, but basically what you're measuring is it's like a spinning wheel. You know, when you have a wheel of a bicycle in your hand, you make it spin. You know, you see its dynamics are going to be very different, and it's because its motion generates an inertia to, you know, a change in the state of motion of that spinning wheel. And so think of that basically. You know, the reality is charge in motion, matter particles, and the inertia that you are measuring and that you are calling mass, referring to as mass, is basically the inertia to a change in the state of motion of that charge in motion. So that's my discussion where you know, I've done philosophy, but I sort of refuse to. It's dualist and it's not dualist. I sort of refuse to enter into a debate on, you know, this is reality and this is, you know, our mental representation of it. Like that there are two things, our mind and reality. No, our mind is part of reality, of course. I do believe in freedom of decision, but it's because, you know, we analyze things and say, you know, I'm going to stop drinking, I'm going to stop smoking, I'm going to do this. And then you do it or you don't do it, depending on your, you know, character and how well you've been trained, and etc. But there's no, you know, for me, reality is and our reputation, they do flow into each other, and it's that system of equations or your representation, that's the language that speaks to me, not pages of words. And that's where I often quote Wittgenstein, maybe a difficult one. Die Welt ist die Gesamtheit der Tatsachen, nicht der Dinge. I think what he meant with that, and he started his structure, is like, don't think too much in terms like, this is real, this is not real. something you measure is real, but at the same time, yeah, it is also a bit of an abstract quality. You know, the inertia to the change of state of motion, whatever. It's a figure on paper, right? If you look at the object or don't measure it or whatever, the object is still there. Don't get lost in sort of such fake or false dichotomies. We see facts, we explain facts, and the world or reality is the whole of these facts. And in physics, the facts are, you know, these equations where you have things that are relative. Indeed, I think it's such a bad term somehow. Einstein should have chosen something better. An absolute. It's not a relative existence or an absolute existence. Okay, I won't dwell on this. I will go to the last slide, and this is one. As said, I started this presentation to sort of make clear to a number of people that please don't categorize me. You can categorize me as a non-mainstream, you know, whatever, or as a crackpot, or, you know, I don't care. But I am not into ether theories, and I quote this thing here because it shows that mainstream and non-mainstream theorists, you can talk a lot about them, but this is a Nobel Prize winner, and I'm going to read his quote there on who believes something like, you know, he fueled, I think it was a remark in the 70s or 80s. And this is what he said, and I totally disagree with it. It is ironic that Einstein's most creative work, the general theory of relativity, should boil down to conceptualizing space as a medium, when his original premise in special relativity was that no such medium existed. The word ether has extremely negative connotations in theoretical physics because of its past association with opposition to relativity. I would say not only that, it's not only because of opposition to relativity. You know, Maxwell knew that the ether didn't exist. We have before relativity theory came out, it's just like Maxwell's equations, they work, and we don't need an ether to make them work. He saw that the speed of light was absolute. So relativity theory basically comes out of you know, classical physics. But let me continue. He said that this is unfortunate because stripped of these connotations, these negative connotations, because of an association, I think, is not with relativity, but just with classical mechanics, classical electromagnetic theory, it rather nicely captures the way most physicists actually think about the vacuum. And there I go haywire. If that's the way that most physicists think about the vacuum as a sort of an ether, well, then I think then most of them have gone nuts, and they are the crackpots and not me. Relativity says nothing about the existence or non-existence of matter pervading the universe. Whoa, he waxes philosophically here. Only that any such matter must have relativistic symmetry. Okay, I get that. That's sort of a space-time signature. I mean, Minkowski spaces, and I said I've done enough. I have enough understanding of vector scalar potential. It's nice to see that, but it turns out that such matter exists. Such matter that pervades the universe. Okay, apart from electrons and positrons, we have some kind of matter that pervades the universe. About the time relativity was becoming accepted, studies of radioactivity began showing that the empty vacuum, of course vacuum is empty, space had spectroscopy structure similar to that of ordinary quantum solids and fluids. Honestly, what are you talking about? I guess it's the theoretical quark gluon stuff, virtual particles, your SOAP theories of. So subsequent studies with large particle X-rays have now led us to understand that space is more like a piece of window glass than ideal Newtonian emptiness. It's filled with stuff. What kind of stuff? I don't see any proven experiments that our vacuum is filled with stuff, but he apparently does. That is normally transparent but can be made visible by hitting it sufficiently hard to knock out a part. So he's talking then about these Higgs bosons and stuff that frankly, for which there are indications maybe that some results of certain experiments might indicate that your model has a higher probability than being right than another model. For me, that's not proof. So he ends this quote with saying that the modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic aether, but we do not call it this way because it's taboo. Frankly, for me, this is hocus pocus. I'm not going to be too severe about it. I guess he's referring to, you know, things that probably make sense. But here, this is, for me, you know, yeah, a great professor, but who is actually falling in the same trap that I see some people, you know, who contact me saying, like, you know, there must be something beyond charge and fields. And where is it then? Well, it's in the vacuum. And what is it then? Well, it's the aether, some kind of properties we can load onto this vacuum. And what kind of properties? Well, you know, matter, some kind of matter that pervades the universe. I'm sorry. I think this is. I will stay polite, but this is this is nonsense. So that will be it for this video. So I have a bit of an unhappy feeling about it because I talked for 1 hour and 40 minutes. I did not script too much. I did not script at all. But I hope at least some people, you know, there's going to be few people who watch it anyway. I have about 100 subscribers. When I look at the analytics of my videos, people usually stay like 10 or 15 minutes into the lecture and then they go. But at least I'm happy I did not go through the trouble of writing it out again and yet another paper, and that I can say now people contact me like, where are you in this, you know, non-mainstream, what kind of theory do you have? Is it based on energy, or is it based on, you know, classical physics like Randall Mills, or which I think he's a crook? Or is it, you know, this kind of thing? I think, you know, my theory is just plain classical mechanics with some sensible modeling of the two stable particles that we know, the electron and the proton, together with their antimatter counterparts, a theory of dark matter, and for the rest, there's not too much mystery left for me. It's kind of a sad conclusion in the sense that and that's also the reason why this might be my last video. I think physics as a science is dead. You know, all that is left is engineering. We know the laws of physics. For me, they look clear. I don't have metaphysical or other weird questions about them. I think it works. I think it explains most, if not everything. Yeah, I should busy myself with my day job and be happy. Because life is good. I wish you a very nice day, a very nice weekend, in this case, if you're watching in the coming days. And maybe I'll see you around. Thank you. Thank you for watching.